Okay. In this lecture, we go back to model selection and we give some more details on the so-called Mallows CP. In particular, we want to give the derivation of this criterion because this is useful to see how the bias variance trade-off works in some detail for linear regression methods. And I will just review what Mallows CP is. It is a criterion that is used to compare models of different complexity. And you can see that there are two main terms. We have the usual residual sum of squares here, and here we have a terms that is going to penalize the complexity of the model. So here we have the number of parameters, and this is the estimated variance of the so-called irreducible error. So the noise, the variance of the measurement error, you could think of it in this way to simplify. And well, okay, 1 over n is not essential, and the idea is that you are comparing models based on this criterion, meaning that if you have two regressions that provide the same RSS, you will choose the one with fewer parameters, because in this way you are minimizing CP. In the same way, if you are considering two models with the same number of parameters, obviously you will choose the one that gives you the smaller RSS. And if you apply this method to choose amongst a model of different complexity, and you start with a very simple model, a simple model will have a few parameters, so D will be small, but RSS usually will be large because the model is not flexible enough. And as you increase the model complexity, you will see that RSS decreases, and this helps minimizing CP, of course, but at the same time there will be an increase of D. So at a certain point there will be no use in increasing D because the decrease of RSS becomes marginal. Instead, you are increasing this part, and therefore CP is going to increase. And the idea is that in an ideal situation, CP would have the typical shaped form. So there is a minimum, and that minimum helps you selecting the best model. Okay, and let's start with some notation. So here are my data, so my observations, and the ith observation is thought of the sum of a true function. This is a true function that depends on my p features and some irreducible error. If you like to start from the regression problem formulated in terms of the joint probability density function of the responses and independent variables, then you can interpret this true function as the conditional expectation of y given the predictors, because this is the optimal regression function, we know, because this one is the regression function that minimizes the squared error. So in some sense is our holy grail. And okay, but if you don't like this interpretation, you can just think of the data as being generated by a true function with some noise. Okay, and we are trying to perform regression on this data using a linear model. Therefore, our predictor is something like FL, and it is a linear combination of the features, the feature variables, and here you have the intercept. Therefore, the total number of parameters that I denote by D is given by P plus 1, because I have the P coefficients for the predictors, beta hat 1, beta hat 2, beta hat P, and then I have the coefficients for the intercept. Okay, it is useful for us to introduce a matrix formulation of the problem. I just take the responses for the first observation, the second one, and so on, and put them in a column vector. I just do the same for the errors, and here I organize my regressors in a regressor matrix X. Here I have a column of ones which is associated with the intercept. So these are the ones that multiply the intercept coefficient, beta 0. I have a column of the first feature for the first observation, the first feature for the second observation, and so on. So this is x1 for the first observation, x1 for the second, x1 for the last nth one, and so on. And this last column is the column of the pth feature. Of course, we are interested in minimizing the sum of squares that, according to this matrix notation, can be written as the difference between this vector and the product x beta. Beta is a vector made of p plus 1, the p plus 1 coefficients beta j, and the least squares estimate is just the vector beta hat that minimizes RSS of beta, the residual sum of squares. And we know that provided that x is full rank, in this case the rank should be p plus 1, the solution, the ordinary least square solution, is given by this expression. If x is full rank as assumed here, the inverse exists and you can compute the ordinary least square solution. Here you have also the vector of the true functions. So this is the true function evaluated for the first observation, for the second, for the nth observation. Finally, once we have the coefficient vector beta hat, we can predict the responses by FL, and the result is x beta hat. And here you can see its expression. And how did I get it? Well, I have x that multiplies beta hat, but beta hat is this one, okay? And this is its expression, so I plug it in here, and I observe that this part that I have marked in orange, this part is made by matrices that are all known, so I can compute this part. It's just a matrix. I will call it H, which stands for hat matrix. So when I compute y hat, I have a square n by n matrix H that multiplies y. So the relationship between the training data and the predicted training data is just H times Y, with this H that we can easily compute. Before proceeding with the derivation of the CP criterion, I need to review some properties of the trace operator. And okay, this will be quick, something that most of you already know and maybe remember quite well, but it is useful to have a quick review. So the definition, the trace of A is defined as the sum of the entries of the matrix on its diagonal, on its main diagonal. So A is a square matrix. A first property is that the trace is equal to the sum of the eigenvalues of the matrix. The trace of the product AB is equal to the trace of the product BA, provided that both products are meaningful. So in this case, as you can see, I'm assuming that A has n rows and B has n columns. So when I change the order, the product can still be done. Okay. The trace is a linear operator, so the trace of the sum is the sum of the traces. And finally, the expectation of the trace is equal to the trace of the expectation. So you can commute between the expectation operator and the trace one. At this point, the first step is establishing some properties for the eigenvalues of H. And we have this lemma, And the lemma tells that assuming that X is full rank, and in particular for us the rank will be D less than or equal to N, then the eigenvalues of H are either 0 or 1, and the number of unit eigenvalues is equal to D, the number of parameters for us. The proof is simple. So let's take an eigenvalue lambda with its eigenvector. So we can write this relationship. Then we pre-multiply both sides by X transpose, and we get this thing. Just remember the expression for H, plug it in here, you get this. There is a simplification. So you get X transpose V equal lambda X transpose V, that is 1 minus lambda X transpose V equal to 0. Now you have two possibilities. If X transpose V is different from 0, then of course here you must have lambda equal to 1. Otherwise, if X transpose V is equal to 0, you can see immediately that HV is equal to 0. So go here and you recognize that if HV is equal to 0, then lambda is equal to 0. So we have shown that if you have an eigenvalue, this eigenvalue can only be equal to 1 or equal to 0. Okay. Other properties of H. For the ones that like to know, H is a type of matrix that is called a projector and enjoys a number of properties. And okay, in this case, the properties are: it is symmetric, its square is equal to H again. Here is the proof, is really very easy. The trace of H, of course, is equal to the sum of its eigenvalues, but since the eigenvalues are all equal to 1 or 0, and the number of non-zero eigenvalues is equal to D, the trace of H is equal to D. And the trace of I minus H, I is the identity matrix, is the trace of the identity minus the trace of H, and therefore it is N minus D. Okay, now we are ready to start with the derivation, and the first step is analyzing the expected value of the residual sum of squares computed on the training data. So RSS is given by this expression. It is a square norm that we can write also in this way. Recall that y is given by the true function plus epsilon, while x beta hat, the prediction, is hy, the hat matrix times y, and y, of course, is given by the true function plus epsilon. Okay, now we are ready. So we compute this expectation. Recall that this is a scalar, after all, nothing more than a scalar. And then we have the expected value of y, which is f plus epsilon. At the beginning, I'm writing f of x, but after some time, I will just drop the x. So it's to make the notation a bit simpler. Minus x beta hat, this is h fx f plus epsilon. I collect the terms in f, so I have I minus h f, and the terms in epsilon, so I have I minus h epsilon. Okay, and this square norm can be written as this product of this quantity transpose this other quantity. And you can see here that you will have 3 terms. So you will have, this is much like the power of a binomial. So you will have the square of this one, the square of this one, and then the cross product. As for the square of this one, here everything is deterministic, also f is deterministic, therefore it can be written without the expectation, and this is the first part. Let's see the square of the second part of this one. Here we have the expectation of epsilon transpose I minus h transpose I minus h epsilon, okay? And since this is a scalar, it is equal to its trace. We will exploit this trivial property. And then we have the crossed product. The crossed product is this one. And I took outside the expectation operator this part, these products that are deterministic. Oh, okay. You should remember that here everything is the cross product is a scalar term. So you would have two cross products because here you're working with matrices, so you would have for instance I minus h f transpose times I minus h epsilon, and then we will have I minus h epsilon transpose I minus h f. But these two crossed products, as a matter of fact, are identical and are also scalar, so I can compute just one of the two and put a 2 in front of it. So this is the crossed product. The deterministic part has been taken outside the expectation operator. Here you have the expectation of epsilon, but epsilon has zero expectation, so this term is zero. So you don't have the cross product. It goes to zero. Okay, next step, let us define the squared bias in this way. So the squared bias is the squared norm of the expectation of y minus the linear predictor. Here there is some computation. I replace y by f plus epsilon, and I do the same also here exploiting the hat matrix. I obtain this expression by collecting the terms in f and epsilon. And again, I can compute this. The crossed product goes to zero, okay, and in the end, I arrive here, okay, and so, okay. Here the term is zero because I take the expectation. This is deterministic, so I can take out of the expectation. Then I have to take the expectation on this one. I minus h is deterministic. I remain with the expectation of epsilon, which is zero. So this term disappears, and I remain with this one. And this one, look here, is just the first term. So the first term that I have here, this is just the squared bias, as we can call it. And the second term is this trace, okay? And so recall that the trace of the expectation is equal to the expectation of the trace. So I compute the expectation of the trace. And at the same time, you know that when I have the trace, I can change the order of the products. And in particular, I'm taking this epsilon transpose and I'm moving it here in the last place. All right. At this point, I go on, and the expectation of the trace, okay, I have to compute this product, and here I have I minus twice h plus h square. Recall that h is symmetric, okay? And recall also that h square is equal to h, so here there is some simplification. I again put the expectation inside, and I have to compute the expectation of epsilon transpose, which is the variance of epsilon, which is in turn sigma squared identity. Okay. Overall, okay, I find that I have beta b squared, the squared bias, plus sigma squared trace I minus h. But the trace of I minus h is the trace of I that is n minus the trace of h, which is d. So this is the final result. The expected residual sum of squares is equal to the squared bias plus this term. Okay, this is interesting on its own, but for us it will be interesting also because it gives a method to estimate the squared bias. Therefore, from here I can say that an unbiased estimator of the squared bias could be RSS. Of course, I don't know the expected value of RSS. I can just compute RSS on my training data, and I will use that as a substitute for the expectation minus this term. So this is a first achievement. We have an estimate for the squared bias, but as a matter of fact, we are interested in the RSS on test data, because this is what is telling me the real performance of my regression function. And how are the test data structured? Well, the test data, we assume that have this structure. They are the true function plus epsilon tilde. Epsilon tilde is a new error vector because we are assuming that the test data have the same axis as the training data, but the only difference is that the noise is changed. So it is like if we had some sense sampled our function in the same x points as we did for training, and the difference being just that the noise is different, of course. So if we had a model with too many parameters that had learned the noise epsilon, when we use this model to predict y tilde, the noise epsilon tilde is obviously different from epsilon. We are assuming that these noises are independent from each other, and therefore it will be of no use having learned the noise in the training data, and the performance is going to be poor. Okay. Okay, so we have explained what's the difference between the test data and the training ones. The residual sum of squares has this expression that can be written also in this way. And now we go for the computation of its expectation. So this is the expectation. Again, I put the true function, but this is the true function plus the noise for the test data. So these are the test responses, and this is the prediction that I obtain using my regression method, my linear regression method. Here I collect the f term that appears here, and I have I minus h. Okay, but I cannot collect as I did before epsilon, because here I have epsilon tilde, that is the noise in the new test data, and epsilon, that is the noise in the training data. So they must be kept distinct. At this point I go on and I compute this expression. Again, we have some cross products, but these are going to disappear because both epsilon and epsilon tilde have zero expectation. So the only terms to survive are these ones. We have the squared bias, then we have the trace of the expectation of epsilon tilde transpose, and the trace of this other term. Here there is the usual game with trace. So this is a scalar, so the trace of a scalar is equal to the scalar itself. And once I've written it this way, I can commute the trace operator with expectation operator, and when I have the trace of a product, I can change the order of the factors. That what I've been doing here. So it was epsilon tilde transpose epsilon, and now it is epsilon transpose. And also here I'm changing the order because I'm bringing this epsilon transpose in the last place. I go on, and again I commute trace and expectation, so I have the trace of this expectation. This now epsilon tilde transpose is a n by n matrix, and its expectation coincides with the variance of the epsilon, because epsilon has a zero expectation. The variance matrix of epsilon we know is a sigma square identity. A similar argument holds here. Here you should also remember that H is symmetric, so H transpose H is H squared, and moreover H squared, by another property of the hat matrix, is equal to H. So I get here, final step, I have the trace of the sigma square trace of the identity, that is n, sigma square trace of d, which is d. Okay, final result, the expectation of the residual sum of squares in test is given by the squared bias plus this term. Now we should remember that we already have an unbiased estimator for b squared. We found it a few minutes ago. Okay, it is here. This is our unbiased estimator. So I'm going to plug this estimator into the last formula. Okay, we have an estimate for beta squared. So we can plug it into this expression, and the point, I divide by n, but this is not essential. So in place of beta squared, I'm plugging its estimate. The estimate we have seen, I have this expression. I have some simplification with n, and in the end I obtain this expression, which is exactly the expression of the CP criterion. So we have derived the CP criterion from scratch. Okay, so this is nice, and you see where it comes from, as a matter of fact. But we have still some question open, and in particular, the question is sigma squared, because the criterion requires knowledge of sigma squared, and if you don't know it, and this is what happens in most cases, you have to estimate it. How can you estimate sigma squared? And here there is an interesting trick that you should keep in mind, that is that you can have an estimate of sigma squared by using a low bias model. If your model gives predictions f hat that are very flexible, and how can you be sure that your predictions are very flexible? Well, you are sure that they are very flexible, that if you have many parameters, possibly more than you really need. So you are using an over-parameterized model in order to be sure that your flexibility is large enough to make the bias negligible. Okay, in such a case, b squared will be equal to 0, okay, or close to 0, and therefore from the analysis that we made before, the expected value of RSS will be equal to n minus d sigma squared. Okay, we can go back and we should be able to find the precise passage. Okay, it is here. So if b squared is negligible, at that point the expected value of RSS is n minus d sigma squared. Okay. And therefore, from this expression, I can estimate sigma squared. I get an unbiased estimate of sigma squared as RSS over n minus d. And of course, I must use RSS because I don't know the expected value of RSS. I can just compute RSS on my training data when I'm fitting the model. And so I have found my sigma square. So this is very useful trick, and we will I think use it next week, because on Tuesday we are going to have a lab session, and you can find the material for the lab session already in the blog, in the Learning from Data blog. Then at the end of the lecture I will give you the link if you don't have it, and we also load the material on Kiro. So you can find in advance the material that we will be using in the lab session next week. A comment on the low bias model. Of course, the low bias model will have many parameters, and therefore it is going to be a poor model, because being over-parameterized, there is a large variance. This is the price to pay in order to be sure that the bias is small, because you have the bias variance trade-off. So if you want a very small bias, you must be ready to have a large variance, and this could seem something. Could seem to you that there's something wrong in using a bad model, but you should not be worried about this. This is still fine, because this is not a model you are going to use for making predictions, but its only purpose is to give you a sensible estimate of the variance. And the relationship that provides the variance is true provided that the bias is small. So the fact that the model is not good at making predictions, it's not going to affect the possibility of using it to estimate the variance. Of course, you must be careful that the overparameterization is such that you can still compute your estimate, because if you are really exceeding with the number of parameters, the overall estimation procedure could become unstable. So overparameterized, but not too much. And you can also try with different levels of overparameterization and see whether the estimate of sigma squared is going to stabilize. So you will try several models with many parameters, and you should see that the estimated sigma squared is not going to change that much. Okay, second remark, the CP criterion can be used also for ridge regression and other linear regression methods, provided that you know the degrees of freedom. But as a matter of fact, for these methods, and we have seen also for it holds also for the smoothing splines, for instance, the degrees of freedom are the trace of the height matrix. So you replace D with the trace of the height matrix, and this is also called the effective number of parameters. And you can use the CP criterion not only for linear regression, polynomial regression, where it is clear what is the number of parameters, but also for regularized linear regression, in which case you will look at matrix H. Okay, that's it. I will stop here.